Lesson 5.2, verifying trigonometric identities. You've already verified them in chapter 4 just a little bit. They were somewhat easy. In this section, they get just a little more difficult, so that's why we have some tips here. Verifying trigonometric identities, work with one side of the equation at a time. Look for opportunities to factor an expression, add fractions, square a binomial, or create a monomial denominator. Look for opportunities to use the fundamental identities. Try converting all terms to sines and cosines. Always try something, even paths that lead to dead ends provide insight. So sometimes whenever you're trying to make one side look like the other, you may go down the wrong path. And if you do, if you have to start over, that's fine. With practice, you'll get to where you know how to take the right path in the beginning, but definitely it takes practice. So let's look at one here. So remember, we're taking one side and turning it into the other side. That's how you verify it. And usually it's easier, as you can tell in number 2, to take the left-hand side and turn it into the right-hand side. So I always just work on the left-hand side. So you have to, on the first step, rewrite the left-hand side. And on the right-hand side, you're going to manipulate what's on the left-hand side to eventually turn into what's on the right-hand side. So secant y, you use your identities, is equal to 1 over cosine y. And then you have times cosine y. And you see how that cancels and becomes 1. So that was pretty simple. Number 6. Rewrite the left-hand side. So somehow we have to get this to turn into 2 cosine squared beta minus 1. Well, my thought is first to factor that. Cosine beta plus sine beta, cosine beta minus sine beta, because it's a difference of perfect squares. But if I do that, I know from experience that's not going to help me turn that into 2 cosine squared beta minus 1. So what I next want to try is changing sine squared beta. If I change it to a form of cosine, maybe that will give me my answer. So I know that sine squared beta is equal to 1 minus cosine squared beta. Use your trigonometric identities. And see, by doing that, now I know that I have 2 cosine squares. And that's what I'm going to have to turn it into the right-hand side. Now make sure you put your parentheses in front of that. Anytime you plug something in where there's a negative, if you don't put your parentheses, you're probably going to forget to distribute your negative. Now you see that we have cosine squared beta and cosine squared beta for a total of 2 cosine squared betas minus 1. And we have the right-hand side. So we have proven or verified the identity. Okay, here, let's see. First rewrite cotangent QT over secant T. I can tell by the right-hand side that I need to split up my cotangent QT. If I break one apart from it, maybe I can use my trig identities to manipulate and get it to turn into the right-hand side. Because I know cosine squared T is equal to cosecant squared T minus 1. You just have to, until you learn your identities, you just keep that sheet and look at it, or look in the front of your book. It's in the very front of your book. You can replace cosecant squared T minus 1, or put that in for cotangent squared T. So I have part of it. Now somehow I have to change cotangent t over cosecant t into cosine t. So I know cosecant t can be rewritten in the numerator as sine t. And cotangent can be rewritten. If I just leave it as cotangent, I'm not going to be able to do anything. But if I write it into sine and cosine, which would be cosine t over sine t, I'll be able to do something with that. So my sine t's cancel. I'm left with cosine t times cosecant squared t minus 1. And that is what is in the original. Number 12. Common denominator. I'm going to add the two fractions together. Tangent b, or tangent beta. Okay, so here's where you're going to have to remember how to add fractions, and we have to apply this to, oops, that's an N right there. So tangent goes into tangent once. 1 times 1 is 1. Bring over your sign. 1 into tangent goes tangent times tangent times tangent, tangent squared. Now, if you need help with that, come see me. We can work on that together. You need to get to where you're faster with that. Now the top turns into, guess what? Secant squared beta. And we're finished. It was that easy. Little trick here I'll show you on adding fractions. Let's say you've got, it's just a little trick here, 1/3 plus 3/4. And this is what I actually did whenever I multiplied the 1 over tangent beta plus tangent beta. If you multiply the two denominators, you get 12. So multiply those two to get your denominator. Take 4 and multiply it by your numerator. Bring down your sign. Take 3, multiply it by the other numerator. And then you get 13 over 12. So that's just a little trick that will help you on all this. Okay, next. Number 14 seems very complicated. It's actually not. Just a lot of writing. I see that can be condensed, and if I condense it, in other words, simplify it, then it will help me. It'll start looking a little bit more like the right-hand side. So, oops, that's a 6 right there. Secant to the 7th x tangent x. When I combine secant to the 6th x and secant x tangent x, that's what I get. Minus, combine the secant to the 4th x with secant x tangent x would be secant to the 5th x tangent x. When I do that, when I simplify that, I see that I can factor out a secant to the 5th and a tangent. You can only factor out what you have. So you can't factor out secant to the 7th because you don't have 7 of them in the right term. When you factor something out, you're actually dividing. So secant to the 7th x times tangent divided by secant to the 5th x times tangent is secant squared x. Okay? And then the second term divided by that, well, it's exactly the same thing. Something divided by itself is 1. And that turns into a Pythagorean identity. So we have secant to the 5th x, tangent x, and then tangent squared x. For when you combine everything, you get secant to the 5th x tangent cubed x, and that is our original. Next, I'm rewriting this over here because I know what I have to do. You don't have Pythagorean identities because we don't have anything squared, but I do know that in order to change this at all, I would have to multiply it by some form of 1, and the form of 1 that will change our denominator, which means really get the function out of the denominator, because we see that we don't have a function in the denominator on the right hand side. We would multiply by 1 plus cosine theta over 1 plus cosine theta. So first outer inner last for your numerator, that will be secant theta plus secant theta times cosine theta minus 1 minus cosine theta. That's first outer inner last. If it helps, you can put this in parentheses and multiply so that you understand that's you either using the FOIL method or you can call it distributing. In the bottom, there's a shortcut for multiplying 1 plus cosine theta, 1 minus cosine theta. And that is the first term squared minus the second term squared. Because it's a difference of perfect squares, and that's how that works. But if you want to use the FOIL method, you'll see that the two middle terms will cancel, and when you simplify, you will get 1 minus cosine squared theta. Okay, in the numerator, secant theta cosine theta is equal to 1. Not 0, but 1. Make sure you put 1. It doesn't just go away because you've got addition and subtraction. So this becomes, rearrange it a little bit, secant theta minus cosine theta, and 1 minus 1 is 0. So that's why it goes away. 1 minus 1 is 0. And then 1 minus cosine squared theta is sine squared theta. Let's see. Yeah, sine squared theta. Oh, and at this point, you're probably thinking, well, I don't know. How am I going to get that to turn into secant theta? Well, I'm going to add together my numerators. But first, to add them together, I've got to change the form. 1 over cosine theta minus cosine theta over sine squared theta so cosine theta is our denominator, common denominator. And remember my shortcut, 1 times 1 is 1 minus cosine times cosine is cosine squared theta. And then remember that's all over sine squared theta. Okay, we have another identity. 1 minus cosine squared theta is sine squared theta. I'm going to put that over 1 because it'll help me to see that I flip and multiply. So these cancel, and this becomes 1. So I have 1 over cosine theta. What is 1 over cosine theta? Secant theta. We have our answer. Number 22. Common denominator. Okay, so if you use my shortcut, remember, let's see, how can we do that? 1 over 3 plus 3 over 4. So you multiply these two, you get 12. Multiply these two to get this numerator, and then multiply these two to get that numerator. Okay, so that's what we're going to do on this one. So I have 1 plus sine theta in parentheses, the whole thing squared, plus cosine squared theta. Okay, if I square 1 plus sine theta, that's 1 squared plus 2 sine theta plus sine squared theta plus cosine squared theta all over cosine theta times 1 plus sine theta. Sine squared theta plus cosine squared theta is equal to 1. So this part equals 1. It's equal to 1. So if it's equal to 1, then I have to add 1 and 1 and get 2 plus 2 sine theta over cosine theta times 1 plus sine theta. I'm going to factor out a 2. Okay, my board stopped working, so I'll save that, pause this, and we'll continue in just a second. Factor out a 2. You're left with 1 plus sine theta. And look at that, that cancels. And 2 over cosine theta is equal to 2 secant theta. And that's our answer. Okay, number 26. So cosine pi over 2 minus x is equivalent to sine of x. Look at your cofunctions. And sine of pi over 2 minus x is equal to cosine of x, which is equal to tangent of x. We're finished on that one. Number 32. Be careful not to mix your x and y's up. Common denominator. Okay, so we know that the numerator for the left-hand side would be cosine x minus cosine y times cosine x plus cosine y. So if we do first outer, inner, last, we would square the first, minus square of the last. Okay, bring over your sign for the other side. Same thing, square the first, minus square of the last. if you regroup, you can see you have cosine squared x plus sine squared x minus cosine squared y minus sine squared y. In the numerator, we've got 1 for cosine squared x plus sine squared x. That's 1. If we factor out a negative 1, here we get, for this, we get this part here, we get negative 1, or negative, cosine squared y plus sine squared y. And that's 1, and 1 times a negative 1 is a negative 1. Well, if 1 minus 1 is 0, and we see that the right-hand side needs to end in 0, we don't have to write anything for the denominator, right? So we have 0. I mean, we can. You can write that out if you want it to look a little neater. Alright, I'm going to have to erase all of that to get the right-hand side. I think I may, well, it's pretty easy, so I'll go ahead and do it. But I need to try to get on through this lesson. So that's secant squared y minus cotangent squared pi over 2 minus y is actually tangent squared y, which is equal to 1. So it looks like for every hard problem we have an easy problem. On this one, all you're doing is you're typing in the left-hand side into your calculator, the y equals function. So y equals tangent 4x plus tangent squared x minus 3. And then below that, you're typing in secant squared x times 4 tangent squared x minus 3, and you're looking at the two graphs. If the two graphs are exactly the same thing, if they overlap, then you know that you have proven the identity through your graphing calculator. So you'll do that on 42 and 44. I will not show that for the sake of time. But if I need to, if you don't know how to do it, just get with me and I'll show you. On this the last two problems here, we're going to use the cofunction identity to evaluate the expression. You remember we learned in chapter 4 that cosine of pi over 2 minus the angle is equal to sine of the angle. And you learned that sine of pi over 2 minus theta is equal to cosine of the angle. So, if you take that idea and look at cosine squared 55, then you know that that's equal to sine squared 90 minus 55, which is 35. And here's where you're going to use your identity, the Pythagorean identity. So two different identities, cofunction identity, and then sine squared theta plus cosine squared theta is equal to what? 1, right? So theta, as long as your angles match, and they do, then that equals 1. So that's your answer to that. Number 54, similar thing. Sine squared 12. If you let's see, which ones do we need to change? You see that 12 and 78 add up to 90. 40 and 50 add up to 90. So you'll want to change one of the two. So let's change sine squared 12 to cosine squared 78. And let's go ahead and write plus sine squared 78. We're going to reorder this stuff. And then sine squared 40 could be changed into cosine squared 50, the complement, plus sine squared 50. And the reason you want that to happen, if your angles match up, and they do, if your angles match up and you've got cosine squared theta plus sine squared theta, then that equals 1. So this would be 1 plus 1 for a total of 2. Okay, so everything I did in this lesson should match up to these problems.